Okay, let's get started with the second part of this introduction. I hope you've had a chance to look at some of those terms, and we'll see more terms now in this part. Okay, so memory is counted, or the size of memory is counted using a number of different units. It turns out they're all trying to describe the same thing, but there are tiny differences. What you might have seen commonly is that the letter K, as far as memory is concerned, is used to represent a kilobyte, which is not exactly 1,000 bytes. It's about 1,024 bytes, which is 2 to the power 10. That's how you get 1,024. Compare this to what you would normally see in other sciences. A kilo is about 1,000 of whatever units we're talking about. So a kilogram is 1,000 grams, and so on. Computer science and electrical engineering, where we use the binary system, it's convenient to use 2 to the power 10 rather than just plain 1,000, just because it's easier to count things when you use powers of 2. So 2 to the power 10 is 1024. It's close enough to 1,000 that we say, okay, that's a kilo. And so when computer scientists say 1 kilobyte, what they really mean is 1024 bytes, not just 1,000. And there are actually some officially recognized letter symbols. For example, when you say 1024 bytes, what you should say is kibibyte. Hardly anyone says that. Most people say kilobytes, but that's what you're supposed to say, and it's abbreviated KIB. So I will try to stick to this notation of a kibibyte. You can click on these links. You will see that KIB, there's this link just popped up. But it's defined in Wikipedia. And so, for example, the other terms like megabyte, which you might have heard about, is approximately 1 million bytes. It's actually 1024 times 1024, so it's a little bit more than a million bytes. And a gigabyte, similarly, is approximately 1 billion bytes. It's actually a little bit more. Okay, so people like Apple will stick to this, the right notation. They will use GIB for gigabytes and MEB for megabyte. Not everyone does this, so I'm kind of flexible about these things. Other things to watch out for: when you see the uppercase B for describing units of memory, that refers to bytes. You will also see lowercase b, and that's used for bits. So be aware of that distinction. So one uppercase B, one uppercase K, and then a B is 1 kilobyte, which is 1024 bytes. On the other hand, you might have seen network connections that have 1 gigabits per second. Notice that lowercase b refers to bits, so that's gigabits per second. If you were talking gigabytes per second, it would be a different unit of speed. Okay, so try to use the IEC standard. There are links to this in this document. Take a look. You may still see the use of lowercase k to mean 1024. What can you do about that? Not much. People are not supposed to use it, but they do, and so everyone does it, so it's no big deal. I think most people know what it means. So 2 lowercase k uppercase b refers to 2,048 bytes, even though officially what you should use is 2 KIB. Okay, so I hope you haven't been confused by that. It's the main idea, if I can go back, is that there are 2 ways of saying kilo. And fortunately, people don't say which thing they're actually referring to. So kilo can be 1,000 or 1024. So that's the source of all this confusion. I hope it's not too confusing to you. Okay. So if you look at the memory hierarchy, a byte can store anything between negative 128 and positive 127. 2 bytes together is usually called a short. Sometimes it's called a short word, but it's just a short. It can represent any number between negative 32,768 to positive 32,767. You might ask why they're not the same number in the positive end and the negative end. There's good reasons for that, and we get into those things in the next year in Computer Science 355. All the details come out there. 4 bytes together, turns out it's not just double of 32,768, it's about negative 2 billion is the smallest number that you can represent with 4 bytes, and the largest number is about plus 2 billion. Okay, so now let's take a look at external storage. So secondary storage or external storage is an extension of main memory. It's not a replacement. You need main memory. You don't always need secondary storage. The fastest memory that you can have on a computer system are the registers. These are very high speed memory locations, and it's used for executing instructions, for doing all the stuff that the CPU needs to do. A little bit slower is RAM, and that's primary storage. It's outside of the CPU. It can be RAM. Actually, there's other kinds of memory too. And then finally, secondary storage or external storage. These are hard drives or flash drives, things like that. Okay, I'm going to go through this rather quickly, look at the basics of how a CPU works. So a CPU executes instructions. We saw that some CPUs can execute maybe 3 billion instructions per second. Well, what exactly is an instruction? Instruction tells the CPU where to put memory, what to do with the contents of memory. So these are the usual things that a CPU will do. So every time it executes, in 1 second it executes 3 billion instructions. Each of these instructions consists of a bunch of different steps, and these are called instruction cycle. Right, I'm going to skip some of the details. These are all in the book. I'm going to just show you pictorially what happens when a processor does something in one instruction. Typically it'll do all these things. It'll fetch the instruction. So this comes from memory. It will have some kind of byte representation of what the instruction should be. It might increment a pointer, store the instruction, and then tell the arithmetic logic unit to do something. For example, it'll tell the ALU to get some data, execute, let's say, a addition or a subtraction. That's what arithmetic logic units do: addition, subtraction, multiplication, division, too. And then the ALU will store this results and tell the control unit, okay, I'm done, go on and fetch the next instruction, and so on. So this cycle keeps going about 3 billion at a time, 3 billion in every second. Okay, so I'm going to skip some of these things, but the main thing you want to keep in mind is that CPUs execute instructions roughly on the order of millions per second, although these days it's up to 1 billion instructions per second, roughly. You might also see the term flop, megaflop, that's millions of floating point, FL stands for floating point, operations per second. And that's usually gives you a better idea of how much work a CPU is doing. The millions of instructions might not give you as much of an indication, but if you have to do a lot of number crunching, the megaflop number tells you roughly how powerful the CPU is, gives you a better idea. Okay, so I haven't gone over the basics of how the ALU works, CPU, the control unit works. Those are all things you want to read up about. I just sort of quickly glossed over it. Definitely take a look in the book and see what these terms mean. And let's stop here for now.